This video is about the undecidability of the classical halting problem. So it's about undecidability of the halting problem. You might have seen the video on the undecidability of a quite special halting problem, that is the problem in which we use the own code as input. In this video we'll consider the more general case, an arbitrary program, an arbitrary input. Does it halt or not? And you might feel that this one is much more important than the other one. Actually, undecidability of the halting problem is you have a program, you want to know whether it will terminate it or not. So this is actually what we are going to look at, and we'll show that this one is undecidable as well. And the result is that there's no hope for a general tool that will always tell us whether our programs halt or not. It's simply impossible. However, for special cases it might work. So the problem we are considering here, I will call it H for halting problem. And the halting problem has two inputs. It has, on the one hand, it has the Turing machine, and on the other one it has the input. So we have two inputs, and I assume they are both binary encoded with some special letter in between, like this one, like this hashtag. But it has to have two inputs. I will call it W for the encoding of the Turing machine and X for the input. And this should be and H should be the set of all these encodings, such that the Turing machine corresponding to the encoding W halts on the input X. So two inputs, W and X, and in this language, so yes, no problem, in this language we collect all the Turing machines together with all the inputs, with all the corresponding inputs, such that the Turing machine halts on this input. Okay, this one is not decidable, I claim. Reason is as follows. We already know that it is undecidable if a Turing machine halts on its own input. Let's assume that it would be decidable if a Turing machine halts on an arbitrary input. So assume we had an algorithm, this algorithm having two inputs, W and X, and this algorithm decides whether the Turing machine with the encoding MW halts on input X. And it says either yes or no. However, if we had this Turing machine, we could easily construct a Turing machine that would decide the special halting problem we have seen in a previous video. Meaning it would be easy to decide if a Turing machine halts on its own input, because we would simply set the input X, which is an input here, we would just set it to be the same as W. And then we would end up with the Turing machine deciding the halting problem on its own code. So we could simply modify or use this algorithm here, put a box around it. We get another input, let's say W prime, and there's something in between, we'll put it here, and this thing would simply put the input W prime to this input and to this input. So we would simply set both inputs to W prime. This one here will be later on called reduction. But actually it's a mapping from these inputs here to these inputs here, and there's not really much to do. We simply feed this input here to both inputs here. And the resulting Turing machine, taking all the outputs, so taking this to yes and this to no, would actually be a Turing machine deciding the halting problem on the own input. So this one would decide the problem K. This would be Turing machine for the problem K. K was Turing machine with own code as input, holds or not. But we already know that this Turing machine, the outer one, does not exist. So we can conclude that this one, the inner one, cannot exist either. And so we know that the general halting problem, H here, is undecidable. So we can conclude that H is undecidable.